Students, welcome to another y video. Today I talk about why is the Pythagorean theorem true. Y is a squared plus b squared equal to c squared. So if you're not familiar with the Pythagorean theorem, I did another video for my pre-algebra class that describes how you use it to solve the sides of a right triangle. But what the Pythagorean theorem states is that for a right triangle, so if I look at this triangle over here, it's called a right triangle because it has a 90-degree right angle in it. But for any right triangle, every right triangle has to observe this equation or this principle. And that principle is that a squared, if you take the side a and you square that value, and you add it to b squared, take whatever b is, and you square that. You add those together, that has to be equal to the third side, the c hypotenuse side squared as well. So if a is 3, and b is 4, if you take those two numbers, square them, add it together, that has to be equal to whatever the third side is squared. In that case, it would be 5 squared, because 3 squared is 9, 4 squared is 16, 9 plus 16 make 25, and that's equal to 5 squared. So it's a little bit of a complicated relationship, and most numbers do not fit nicely into this formula because it's a slightly complicated sort of formula for it. So we're not going to look at examples of how you use it. Today I'm going to show you why is this true, and what we're going to do is we're going to do a little proof of the Pythagorean theorem. I'm not going to do it super formally, just going to try to illustrate the idea of how it works. Again, I believe that if you see why it's true, it'll help you remember it a little bit better, and if you can see why it's true, it gives you a little bit more insight into, the mathematical formulas, why it is the way it is. It's nice to look at it, memorize it, and be told it, but it's also nice to be able to see it for yourself and believe it and understand it, and that's kind of the idea of what a proof does. So it's not super hard, and I'm going to show you the easiest one that I know of, or the easiest one I think. And again, there's lots and lots of proofs of this in different ways to show that it's true. This, I think, is just, in my opinion, is the simplest way. So let's say we start with a right triangle down here. So pretend I'm a good artist, and let's just say, that side's a right angle, this side is length A, this side's length B, and this side up here is length C, the hypotenuse. So how this proof works is sort of like in my video, which I talked about why foiling is true, but if we take a lot of areas of triangles and squares and stuff and add them together, it shows that it adds up as well. And kind of, if you think about why you would do this, figuring out why to do it this way is kind of that's the hard part of a proof. It's very, it took people a while to actually formalize this relationship. People understood the relationship before they could prove that it's true. So the proof is not something that's easy to figure out. But once you see it, it's kind of, oh, that makes sense, and that's kind of what I'll try to do. So essentially what we're going to start off doing is we're going to make a square. We're going to just sort of hyperimpose a square on top of this triangle, sit it on the side of it, basically take the length C up there, the hypotenuse, make a square out of that C. That's a little bit off. Crap. All right, let me start over. Sorry about that. Okay, we got my right triangle. This side is A, B, and C with the right angle. And so what I'm going to do is I'm going to build a square on top of it. So I want another length C perpendicular to that C. So I need a little bit longer. And then over here we're also going to have another side of length C to form a square. And then again another right angle to connect to my square. So I'm just building a square on top of there. Again, you might not, for right now, don't ask why. There's a reason, I promise. And so again, these sides would all be length C because that's a square that I built. Well, now if we built a larger square, if you look at that, it's sort of like a tilted square. Say we box that thing in with a square that's flat along the ground, or basically we went all the way up to there and then built another line over there, came down like this, and sort of enclosed that sideways square with another larger square, right? And then the proof looks at the areas of these segments and seeing how they all fit together. So anyways, before we look into that, we need to find all the unknown sides that I've drawn. And some of you might be thinking to yourself, well, all those triangles that you drew kind of look like the original right triangle, which they in fact are. The reason that's true, again, it would involve a little bit more of a formal proof. But if you look at the two angles of your right triangle, so whatever, I'm going to use a color here. Let's say we had, I'm going to draw this angle in red. This angle actually will match up with this angle and this angle over here and this angle over here. So again, those are all the same angle. Why is well, I can explain that in just a second. Also, the other angles in the right triangle, if you look at the smaller angle over on the right hand side down here, that should be the same as this angle and the same as this angle and the same as this angle. And since they're all right angles, the reason why we know that the corners of these are all right angles is because I constructed a square, and a square has to have, you know, every angle in the square has to be a right angle. Again, another property of square. Basically, the reason that we can figure out the rest of these sides is because all these triangles are identical triangles. Actually, they have all the same angles. And if if you really wanted to sort of prove that those angles all line up, it can be done pretty simply. If we look at down here, over here on the left, if we look at these red and the blue angle over there, and additionally there's a little right angle in between there. Well, the blue angle plus the red angle plus this right angle there, that forms a straight angle if all three of those are added up, because that would be a straight line, 180 degrees. So basically, the red plus the blue plus 90 adds up to 180. And so really the red plus the blue have to make 90 the difference between the whole 180 angle and that right angle. So basically blue plus red needs to be 90. And since in my right triangle, whatever red is some angle, another basic property of right triangles is that those two angles have to add up to 90. Basically, if this red is something, this blue over here has to be 90 minus that something, and that will match up with this other blue angle and so forth. So kind of that's sort of my informal explanation as to why. Basically, at the end of the day, all these triangles are all the same dimension. So this triangle over here on the left right triangle up there, this length would be B, just like the base of our original right triangle, where this side over here would be A. This side here would be B, this side would be A. And then this side would be B, and that length would be A. So essentially, all those little lengths that kind of are created by this square being put together, they're all basically that same right triangle, just like if you can picture the one that we started with over on the left-hand side over here, it's rotated and then rotated and rotated. So those four triangles are all the same size. So anyways, now we have all the dimensions. So how the proof works is we take the area of the entire rectangle, or the entire, actually what you might notice is that this is a big square that circles, goes around the smaller square. But essentially this side over here is A plus B. If we look at this length down here is also A plus B. So if we want to find the area of the entire square, the big square, that would just be A plus B times another A plus B, or A plus B squared. So let me go ahead and write that over here. If we take those values in red, we would get A plus B times A plus B, or A plus B squared. So that's one way of looking at the area. There's another way we could examine this entire area, as if we look at the area of this whole thing, it should be the sum of all those shapes in there. So we have 5 little segments, 5 different portions of area inside the thing. We have the area of our square, our sort of sideways square in the middle. And since that square has dimension c by c, that square would have area c squared. And then there's 4 other triangles on the outside, which are all identical triangles. So like if we look at this triangle down here, that has some area. And this triangle over here would also have an area, and this would have the same area, and then this one over here would also have the same area. So we'd have 4 triangles all with equal area. And if you're thinking of, well, that would just be 4 times the area of one of the triangles. So, well, area of one triangle, one basic formula for area of a triangle is 1/2 base times height. And in the right triangle original on the left, the base would be B, the height would be A. So a nice thing about right triangles is the area of them is actually just 1/2 of A times B. You take the two legs, multiply them together, multiply by 1/2. But essentially the area of one of those blue triangles would be 1/2 A times B. And since we have 4 of those, if we want to find the area of all 4 of them, we would just take the area of one of them, which is that thing in blue, and multiply it by 4. So essentially, that's kind of how we examine the area of all those individual pieces. So at the end of the day, the area of the larger red circle, A plus B quantity squared, that needs to be equal to the sum of those 5 shapes, which would be C squared plus 4 times A times B. So if I fill in kind of an equation that logically explains my idea, the big square, A plus B quantity squared, that was the area of the larger square, has to be equal to the sum of all those parts. So C squared plus 4 times 1/2 AB squared, because C was the small, C squared was the smaller square, and then this was the area of the triangle. And since we had 4 triangles, we multiply by 4, and we add all those 5 pieces up, and that should be true. So these two things have to be equal because it describes the same amount of area for both A plus B quantity squared and C squared plus 4 1/2 AB. So now to show the Pythagorean theorem, if we just simplify this a little bit, we'll see why the Pythagorean theorem comes through. But if we FOIL A plus B squared, remember that would be A plus B times A plus B. Remember, that is not A squared plus B squared. That is never true. That's called a freshman's dream. It doesn't work. Bad. You have to FOIL. If you don't know why I have to do FOIL here, go back and watch my video on why do we have to FOIL. I just did that. I just uploaded that a second ago. But basically, we get A times A is A squared, then plus A times B, and plus B times A. That would be plus 2AB. And then we would get B times B is B squared. So on the left-hand side, if we expand that A plus B quantity squared, we would get A squared plus 2AB plus B squared. On the right-hand side, we have C squared, and then we have 4 times 1/2 AB. So 4 times 1/2 is just 2, so we get C squared plus 2AB. And so what we get, if we just rewrite that, we get A squared plus 2AB plus B squared is equal to C squared plus 2AB. And so what some of you might be screaming in your heads as well, we have the same thing on both sides. There's a 2AB on both sides. So what we could do is we could subtract 2AB from both sides of our equation. Of course, that's a thing we're allowed to do with an equation. They would cancel each other out, and what are we left with? We're left with A squared plus B squared is equal to C squared. So sort of the logic behind this is that we're examining one portion of area, a large square, and that has to be equal to the sum of the smaller portions of area. That's just sort of a basic idea. You know, if we add a bunch of things up, that's got to be equal to the total. So both sides of those equations had to be the same. And so if we just use a little bit of simplification on both sides, we see that at the end what we get is sort of the Pythagorean theorem, which describes that relationship between the 3 sides of a right triangle. And again, if you want to know how to use it to solve a triangle, that's my other video on how to solve triangles using the Pythagorean theorem. But hopefully this helps you remember why it's true. But basically, A squared plus B squared equals C squared is just a divine law having to do with right triangles, and it works for any of them. It's got to hold true, and it just describes the relationship between the 2 legs, the length of those 2 sides, and then the length of the third slanted side, the hypotenuse. Hope you enjoyed. Hope it made sense. If you are still confused, have any comments, make sure to leave it in the comment section. Give me a like if you like it. And if you don't, I'm always up for constructive criticism. Have a great day. See you guys in my next video.